Okay, these are the answers to 2004, number 2. The average is a 5, so on the medium side. Okay, you have a solid disk of unknown mass and known radius r, blah, blah, blah. Be really careful because I think at some point they ask you to find I, and they should have said, they shouldn't have called it a disk because you will lose out on a ton of points if you say, oh, it's a disk, I is mr squared over 2. Okay. It's just so the disk does not have uniform mass or something. You cannot use the plug and chug formula for a disk. Okay. Question A says, calculate the linear acceleration A of the following block in terms of the given quantities. And what is a little confusing is they give you, oh, I didn't highlight it. Okay, they give you time, they give you distance. It is rare that these kind of problems are constant acceleration physics Sudoku, but because they give you time, that's a big fat clue that this is not forces right now and torque or energy even, because they gave you time. So time is a big fat hint that it's a physics Sudoku. V naught is 0. We don't know V final, but we know X naught is D and X final is 0. So you know more about the location. So I'm not going to set up the whole chart. But that's a clue that we're going to use the position function because we care about time and we know initial and final position. So the final location is 0. The initial location was D. It started at rest, so that's nice. That term goes away. And we're looking for A, and you know T. I didn't bold it. And so they're calling anyway, I'm getting a little flustered because clearly this is going to give us a negative time. But I don't like in their PDF rubric they called X final D. They called down positive. So I think we're going to be fine. So assume A is negative. So T squared is going to be minus 2D over A. So T is the square root of minus 2D over A. So that looks like it's an imaginary number. But if A is negative and you plug in a negative value, you are going to take the square root of a positive number. Oops, we're solving for A. My bad, sorry. Okay, so A is 2D over T squared. Done. That was worth 2 points. So 1 point was for understanding, oh, I need to use constant acceleration equations and choosing the right one. And then 1 point was for applying the right values, plugging them into the constant acceleration equation. Okay, so this is a fake lab. So you take 4 data points. What quantities should be graphed in order to best determine the acceleration of the block? Okay, in 2025, you get Desmos. So you can just plot these things in Desmos and do a curve fit. That's what I assume you will be doing. But I'm going to show you the way we used to do it. So we know that acceleration is minus 2D over T squared. And then you want to look at, okay, I know D and I know T, right? The bigger the distance, the greater the time, but it is not directly proportional because time is squared. So what you want to do is think of this kind of like a U substitution. I guess I have room to do this here. So we want to find A. So A, and I'm just going to ignore the negative sign, right? A is going to be, if we think of it as A is the ratio of 2D over T squared, then if we graph 2D on the y-axis and t squared on the x-axis, then A is the slope. Okay, so go back and find the module that is Fake Labs. And that will, I'm not going to go through this now because it would make the video too long. But basically, when things are not linear, you have to think of, I'm going to replace the quantity, think of it like a U substitution. T squared is now X, and 2D is now, sorry, I'm trying to get different colors. 2D is now Y. And then rise over run will give me the slope. Okay, so that, and there's more than one way you could do it. You could graph D versus T squared, and then, then you can also compare this to the equation of a line. So D is A over 2T squared. So if you compare that to, sorry, let's do it over here. D equals A over 2T squared. So if I graph D on the y-axis and the quantity T squared on the x-axis, then my slope is A over 2. So there's more than one way to do this, but what you can't do is you can't graph, you can't graph D versus T, because then you would get a parabola and your brain can't do a curve fit. Desmos can, but your brain can, or on, with a ruler, you can find the slope of the line. That's what we're trying to do. I'm not going to talk about this too much. Go back and go find the module on Fake Labs and linearization. Okay. So to save time, I just copied the rubric solution, but I'm going to talk about it a little bit. So again, you could graph 2D and T squared and your slope is A. They chose to model, I'm going to graph D versus T squared. You always want to ask yourself, should there be a y-intercept or not? Because 90% of the time there's not, but then you really don't want to assume, go on autopilot and get stuck on the ones where there is a y-intercept. But if you look at this, if you plug in T equals 0, you get D equals 0. So yes, 0, 0 is a legit point. The other thing you want to know is, so you get a point for basically plotting the points. That's a free point. Be really careful. You get a point for plotting the data correctly, right? But you have to, this is what I see people not do. You've got to label the axes. So you have to say this axis is T squared. You have to say the units are second squared. Like, that is not optional. You have to say this is D and the units are M. That is a free point. So you have got to do that. Please do that. People drop the units, or people just don't label what they're graphing. Again, watch the linearization if you want to see how to spread the data out. Often there's a point for making sure that the data isn't too bunched up, because the more room this takes up, the more accurate your line is going to be. Okay, and then you get a point for picking the best fit line. And that's what I wanted to talk about. Notice that the goal is not to draw the line that goes through as many points as possible. The goal is to use your eye to kind of average out the points. So these 2 points are above the line. This point is below the line. I actually think their line was maybe a little too shallow, because we have 3 points above the line and 1 point below the line. So I think they could have made it a little bit more steeper. But don't try to get the line. This is real data. My point is, it's not going to go through all the data points. Your brain is going to be really good about eyeballing using a clear ruler that you are allowed to bring into the AP. kind of averaging the data out. And so we assume it's systematic. No, we assume it's random data, so that some points are going to be high and some points are going to be low, but your brain's going to pick the best line. Okay. Again, go watch the linearization, dig into that if you want to know how to spread out your data and plot your data. So that was 3 points. And then we're going to use the graph. So that means, hey, calculate the slope and connect the slope back to the concepts to find the magnitude of the acceleration. Okay, so it says use your graph. And so again, in the old school AP Prop Fake Labs, the slope meant something and the y-intercept could mean something. In this case, we're going to find the slope. So I'm going to briefly say what not to do. You just took all this time to make this graph. That was not just to prove you could make a graph. Do not go back and take the difference between any 2 points. Don't take delta y over delta x up here. Let me show you why. Because if you had chosen, sorry, can I make a line? Yeah. If you try to connect these 2 points, that's way too steep. So once you have plotted all of your data points, ignore the data points. What you are looking for are points on the line that are easy to read. So this is the point 1.5 comma 1.5. This is the point 1 comma 1. This is the point 0.5. I mean, it's easy because the slope is 1. Definitely use the 0.00 if that's what it goes through. But that's what you're looking for. This made it a little too easy, but you're looking for spots where the graph hits one of the edge of a square of the grid, so that you're not trying to extrapolate what those numbers are. Find points that you can read easily. Okay, and then use those to take the slope. Make them as far apart as reasonable, because the closer they are together, the greater error you're going to have, and that being off by 0.2 is a bigger percent of this triangle than of this big triangle. Okay, so again, go back and dig into the it's called Fake Labs or linearization module. Okay, so I know y'all take the slope, so trying to save time. So once you pick the 2 coordinates, take y2 minus y1 over x2 minus x1. Slope has units in physics. And then you got to figure out what that slope means. So again, since this is y and this is x, what's in front of that is your slope. So your slope isn't a, your slope is a over 2. So set the slope equal to a over 2 and then solve for a, and don't forget your units. Okay, just quickly, I assume in 2025 and beyond, you would plot those points in Desmos and do a curve fit, and boom, you have your slope. But you need to know what the slope means. Or it would be a parabola and you would do a parabolic fit. But what your coefficient for t squared would not be a, it would be a over 2. Okay, C. You don't know how many points everything is worth on the AP. You don't know there's a hidden 4 points there, which is a hint that it's not an easy problem. This is really unfortunate, because I think what a bunch of people did, I bet, and when I'm given this as a practice AP, people are like, oh, it's a disk, I equals mr squared over 2. Boom, I'm done. I've got enough other things to think about in the AP, and they don't realize that they left all the points on the table. So I will work this out offline and then go over it just to save time. But a big fat hint is we've got one object that is rotating faster and faster and faster, and we have a second object that is translating faster and faster and faster. Okay, so I like that the AP doesn't spell out, use energy to do this or use this to do that. But I don't like if they kind of misdirect you and getting you to think about kinematics is not helpful in terms of forces. I wish they had said draw a force diagram for both objects, just to give you kind of a little bit of a lead into what you're going to do. So back in a minute. Okay, so my forces did not end up being very pretty, but focusing on just the block, it has weight. There's a tension. Do not assume that the tension equals the weight. That is not true because it's accelerating down. So we know the weight is bigger than the tension. I highly recommend that you draw a little acceleration vector to remind you that down is positive, up is negative. The rope molecules are evenly stressed, so the tension is up on the block but down on the pulley. These two purple tensions are the same because the molecules are going to distribute the stress. There's a second tension, but it's supporting the pulley. It's acting at the pivot, so that's not going to cause any torque. The second pulley also has weight. Make sure you have subscripts because they're not the same. That's also acting on the pivot. So the only thing that's causing torque is this tension. And then we're doing winning minus losing so that we don't have any floating minus signs around. So we're defining counterclockwise as positive and down as positive. Okay, so that's your force diagram. And then we're going to analyze the forces. Okay, I highly recommend, based on the other videos that I've made, where I was just kind of like, let's try this because it's looking for linear stuff. It was confusing. And so I just recommend, if you know, like, I've got something that's translating, I'm going to have a linear column. I have something that's rotating, I'm going to have a rotational column. Optional, but I'm going to have a miscellaneous column so I don't forget to use A equals alpha R or calculate friction. Then it's all in one spot. And if you get stuck, you'll see this problem, just like the physics Sudoku. You got to figure everything out. If you just know that you need all these things, then you're not going to go down the linear path and then go, I don't have enough information, or just assume, oh, the tension is the weight or something. Make all three columns to begin with. Okay. Linearly, you got the sum of the forces equals MA. Weight is positive because we define down as positive. Rotationally, you have sum of the torque equals I alpha, and then the rope is not slipping. So the rope that is connected to the thing that's translating A is equal to alpha R. Okay, so I'll finish filling this out, but I would say just make the columns if you know you're going to be using rotational and linear. Okay, so rotationally you have one torque, it's only the tension. So you have RF sine 90 equals I, that's what you're looking for. Don't plug in I equals MR squared over 2, you are looking for I. Alpha, and then alpha is A over R. Okay, we are looking for I, so actually let's solve this for I. So I equals R squared over A times T. And then let's solve this for T. So T is going to be mg minus ma. I just changed positions, these two. So I is going to be R squared over A times mg minus ma. You could factor out an m. And then let's actually divide, well, let's do it in two parts. And this might, you could probably stop there, but let's divide through by A. So it's G over A minus 1. I don't know if I like that better. And this doesn't maybe feel very rewarding, so I kind of like this better because you know, remember the toilet paper lab, you know it's accelerating at less than 9.8, right? Because this block wants to fall at 9.8 and tension is holding it back. So you know the acceleration has to be less than 9.8. So that should at least make us happy that our rotational inertia can't be negative. So G has got to be bigger than A. right? And these have the right units. We're subtracting things that have the right dimensions from each other, so that's a good sign. And we also have the right units of I, right? Because in terms of units, this is meters per second squared, and this is meters per second squared. So we're just going to end up with mr squared times some, fraction, some ratio. So that feels good to me. Yeah, and I'm just checking my work with the answer. Okay. So in terms of the points, super quickly, before we go to the logic question, you got a point for kind of combination of understanding that you needed to use torque and understanding there was only one torque. You got a point for understanding this string was not slipping, right? So minimum, you're running short on time and you see something where no slip applies, write that down. You get a point for correctly applying Newton's second law. I know that seems like they're saying a point for correctly applying. So, it looks like maybe you could start with this. I recommend that you don't, that you say, this is the fundamental idea I'm using, impress the AP reader. Like, don't show a million algebraic steps, but fundamental concepts, like I'm applying Newton's second law, and then this is what it is. Will help the reader find your work. And then you got a point for solving for T, it looks like, I don't want to, which seems odd, and then a point for solving for I. Oh, no. The solving for T was not a point. They were just telling you what they were doing. So you got a point. This makes more sense. You get a point for actually pulling everything together and finding the final answer for I. Okay, so there's a lot of hidden points there, and 4 points, right? And then what was the average? The average was 5. So that was where, almost all of the average points came from. I mean, that's not where people got them, but okay, sorry, I'm babbling. All right. So then the last question, again, I think then 2025, they're really trying to make sure people understand what is going on and not just do the math out. So, what they're saying is you could do this fake lab and you could find I. So somebody does the experiment, they make the graph, they calculate I, and then they take the pulley out and they compare that to mr squared over 2, I guess, and they found that the actual rotational inertia is bigger than the measured. So what that means is, let's think about that. When you measured it, you thought I was smaller than it really was, okay? Which means that it was accelerating faster than it should be. Does that make sense? I found it, I got to think about this carefully. You got a measured I was too small, and they did that on purpose because the default people, when they're asked to explain, like come up with a source of error, the default is usually, hey, there was friction. So they're doing this on purpose so that you can't just go on autopilot and go, okay, there might have been friction. But that makes it really, really hard. So I was too small. And so I want you to think carefully about these, come up with a source of error, but I don't want you to overthink them because it's not a real lab. You don't know the situation, so you can't say, I mean, it's fake because you're pretending you're in the lab. So I'm babbling, but what I'm trying to say is what they want you to recognize is, okay, I is too small. Which would mean the acceleration is too large. Okay, so then just come up with a reason that the acceleration is too large. And I know this seems maybe like a smart butt answer, but you could, what would make the acceleration to appear to be larger than it should be? Maybe you anticipated the landing, so your time is too small. So come up with a reason why the time would be too small. The stopwatch, I stopped the stopwatch too soon. Oh shoot, we didn't measure time. Did we measure? Yeah, we did. We measured time. So the times were too short. What else would make the times too short? Well, maybe the distance D was shorter than you thought it was. And again, I don't like these answers because to me, it sounds like you're coming up with excuses for like, I wasn't careful. What they're trying to get you to understand is what measurement went wrong and in what direction in order to get the result I did, because that shows that you understand how all of these things are connected. Okay. So somehow the time was too small. Somehow the distance was less than it should be, right? And then the time was that would make the time too small. The answer that they gave on the PDF was a little bit more complicated than that. They were like, well, if the rope was really, really thick rope, then your torque was, quote, bigger than it should have been because your lever arm was bigger than it should have been. Again, that seems like a little bit of a stretch to me. But again, they're just wanting you to see the relationship between the variables. But they specifically noted you could not say there was friction because friction would have made the time bigger than it should be. So quickly, we're almost done. Thanks for your patience. This was worth 2 points. So let's see, for a reasonable analysis, that indicates either the mass or radius is greater than given. Oh, okay. Anyway, I'm not going to dig into this more. Yeah. There's a little bit of like judging expertise on just be logical, figure out how are these relationships connected, what variable would it change in order to make the result off in whatever direction it was off. Okay, hopefully that makes somewhat sense. And again, if you are like I did and I'm stuck on this fake lab stuff, go back and do the module on fake labs. So that is it for torque, and thanks for listening.